So, like, if you ask an AI to write a Shakespearean sonnet about a toaster, it is, it's just pure magic.
Yeah.
It gives you this brilliant, fluent poetry in, about 2 seconds.
Right, yeah. It feels like you're talking to a genius scholar who just instantly understands, like, the nuance of language and creativity.
Exactly.
Fun.
But then you ask that exact same brilliant AI to do a seemingly basic real-world task. You say, hey, go online and buy me a specific black waste bag under $20 with a 4.5-star rating.
And it just completely falls apart.
Totally. Suddenly that genius scholar turns into a toddler trying to parallel park a minivan. It gets confused by the website, clicks the wrong buttons, gets stuck in a loop, and just, fails.
Yeah, the illusion of capability just shatters the moment the model has to actually interact with our rigid, multi-step environment.
Yeah.
We love to think of these models as intelligent agents, but the gap between chatting in a text box and actually doing a task on the internet is, well, it's massive.
It really is. So today we are exploring a state-of-the-art breakthrough that bridges that exact gap. Welcome to the deep dive.
Thanks for having me.
We are looking at this really fascinating paper from researchers at ORO, AI, and Dynamical Systems. And they aren't fixing this problem by just, blindly making the AI's brain bigger or shoving more text into it.
Right.
They are throwing these models into a continuous crypto-funded gladiator arena to fight it out over shopping tasks. The research is called Bittensor Agent Arenas as a Trajectory Primitive. And by the end of this deep dive, you are going to understand the radical new way AI is being taught to navigate the real world.
It really is a fundamental shift in philosophy. We are finally moving away from having giant language models just talk to themselves in a vacuum, and moving towards small, hyper-capable models trained on the verified, battle-tested traces of these continuous arena competitions.
Okay, let's unpack this, because if we want an AI to be a reliable personal shopper for you, my first thought is, why can't I just feed it the entire internet? Like, let it read every e-commerce site, every shopping blog, every Wikipedia article about retail, and just learn how to shop.
Right. I mean, that's the intuitive approach. But reading about shopping isn't the same as executing a shopping task.
Yeah.
To successfully interact with the digital environment, the AI needs what researchers call a trajectory substrate.
Meaning what, exactly?
Think of it as the breadcrumbs of decision-making. It's not just a matter of the AI knowing what a black waste bag is. It needs step-by-step supervision on the mechanics of the task.
Like the actual clicking and searching?
Exactly. How to issue a tool call to a search bar, how to reason over a really messy, noisy list of product results, how to track soft constraints like shipping costs across multiple turns,
Right.
and crucially, how to recover when a search hits a dead end. That requires a very specific type of multi-turn trace data. And historically, the two main ways the industry tries to get that data they've totally failed us.
Yeah, the paper mentions two specific failed methods. Let's look at the first one, which is fully synthetic data. This is where developers just use a massive cutting-edge model like a GPT-4 or something to generate the training data for a smaller model, right?
Yeah, that has been the industry standard. You prompt a massive model to role-play both sides of the interaction. You tell it, pretend to be a user asking for a product, and also pretend to be the agent searching for it.
Sounds easy enough.
It does, but when you do that, the generated data inherits all the hidden biases of the synthesizer.
Right.
And more dangerously, it suffers from model collapse.
Collapse.
Yeah, it means it flattens out the long tail of the data distribution. The synthetic AI just learns the most average, statistically safe way to solve a problem.
Oh, I see.
So it creates these highly sterile, predictable scenarios. It completely loses the ability to handle the weird, messy edge cases that happen constantly on the real internet.
Okay, so if generating fake data makes the AI too sterile, what about the second method? Like just using production logs. Taking the real-world, unfiltered telemetry from actual deployed shopping bots that are currently out there trying to buy things.
That sounds like the perfect solution in theory because it contains all that real-world diversity. The problem is that production logs are totally unjudged, and they're notoriously contaminated by shortcut behavior.
What do you mean by shortcut behavior? Like the bot is cheating?
Essentially, yes. It's when an agent accidentally stumbles onto the right answer through completely illegitimate, hallucinated reasoning.
Wow, really?
Yeah. It might click the wrong link, misread the price, and somehow still land on a bag that happens to be under $20. If you take that log and train a new model on it, you aren't teaching it how to be a smart shopper.
You're teaching it to be lucky.
Exactly. You are actively teaching it to hallucinate and make wild guesses.
I'm trying to picture this. It's like trying to teach a teenager to drive.
Mm-hmm.
If you use the synthetic data approach, it's like sitting them down in a perfectly programmed driving simulator video game.
Right.
The weather is always sunny, the other cars are perfectly polite, they learn the basic rules, but the second you put them in real-world traffic, they freeze and crash.
That's a great way to look at it.
But if you use the production logs approach, it's like making that teenager sit in a dark room and watch hundreds of hours of random dashcam footage of terrible drivers running red lights, swerving across lanes, and cutting people off.
Exactly. Neither of those methods is actually going to teach them good, reliable driving habits.
Right.
What's fascinating here is that the true bottleneck for making small models highly capable is no longer the algorithm you choose. It's not even how many parameters or how big the model's brain is. The absolute bottleneck is getting judged, high-quality, multi-turn data.
Which brings us to the gladiator arena. Because since synthetic data and production logs both fail, they had to engineer a completely new machine to manufacture the perfect data.
Exactly. They didn't just build a new static data set, they built a living economy. They deployed what they call ORO Subnet 15 or SN15 on the Bittensor network.
Okay, so how does this arena actually function on a day-to-day basis?
So SN15 runs a continuous benchmark called ShoppingBench. It's a complex, multi-turn tool use test specifically designed for agentic commerce. Independent developers from all over the world, who are called miners, submit their custom-built AI agents into this arena.
And then what?
These agents are thrown into a nonstop race against a rotating massive bank of shopping problems.
And these independent developers aren't just donating their time and server costs for bragging rights, obviously.
Oh, not at all. They are financially motivated. They are continuously paid in crypto tokens based on their agent's performance.
Wow.
Yeah, the network has validators that reach a consensus on the scores and distribute the emissions. But the genius of the system is the incentive structure. Miners only get the big rewards if they discover successful shopping policies that their competitors haven't figured out yet.
So it's a race to be unique, not just accurate.
Exactly. It creates this intense discover then share pressure. When a miner wins the daily race, their specific source code is embargoed.
Meaning they keep it secret.
Right, they get to reap the rewards for that day. But the very next day, that code is shared with the rest of the network. So the entire ecosystem is forced to constantly push the boundary of what's possible just to stay ahead of the pack.
Okay, I have to push back on this whole setup, though. If you tell a bunch of developers, here's a benchmark, and I will give you financial rewards if your bot beats it, human nature kicks in.
Oh, absolutely.
They aren't going to spend months building a genuinely smart, generalized AI that understands the nuances of human commerce. They're going to build something that memorizes the specific test answers, or they'll find a loophole in the greeting system to just farm the crypto tokens.
This raises an important question, and it's exactly what the researchers anticipated. They knew they were inviting the smartest people on the internet to try and game their system. So they built two ingenious safeguards to ensure the data coming out of this arena is actually useful for training real AI.
Okay, what's the first safeguard?
The first is an LLM reasoning judge.
How does a judge stop them from gaming the test?
Well, in most benchmarks, you just look at the final answer. Did they buy the bag or not? In this arena, every single trajectory is scrutinized. An independent language model acts as a judge and actually reads the internal think and tool call trace of the agent.
Oh, so the AI literally has to show its math.
Exactly. The judge issues a reasoning quality coefficient. If the agent gets the right answer, but its internal logic was nonsense, or it stumbled upon the bag by accident, the judge flags it, and the miner doesn't get paid.
So they can't just brute force their way to the right URL. They have to prove they logically navigated the website to get there.
Yes, exactly.
What's the second safeguard against cheating?
They call them leak cluster guards.
Reclusters.
Yeah. The biggest risk in any test is memorization. To stop miners from just downloading the problem bank and memorizing it, the rotating problem suite groups similar queries together.
Give me an example of how a leak cluster works in practice.
Let's say the original problem the AI trained on was find a red shoe under $50. The researchers will take the held-out test problem and phrase it as locate crimson sneakers below $50.
Okay.
The system groups these together. The researchers are preventing what they call surface form drift, which just means changing the synonyms and the sentence structure from smuggling the answers into the open pool. The AI can't just memorize flashcards. It actually has to understand the underlying concept of a cheap red shoe to pass.
That is incredibly clever. So you have this arena running 24/7. The miners are fighting for tokens. The reasoning judge is forcing them to show their work. And the leak clusters are making sure they don't just memorize the test.
Exactly.
This creates a massive fire hose of data. The paper says between 12,000 and 27,000 trajectories every single day.
Yeah.
But clearly, you can't just take that raw fire hose, attach a hose to a blank AI model, and turn it on.
No, the data is far too messy for that. You have to sift the fire hose. The researchers built a strict structural quality filter. First, the data goes through format normalizations, and they instantly drop any trajectories where that reasoning judge gave a low score.
Makes sense.
They also deduplicate the data and rank it based on structural quality.
Things like how deep the search went, or if the agent actually double-checked the price before checking out.
Exactly. But the most crucial part of this entire filtering process isn't just dropping the bad data. It's splitting the good data into two very distinct categories: Axis A and Axis B.
Axis A and Axis B. This feels like the turning point of the whole paper. What is the fundamental difference between the two?
It all comes down to who or what is actually driving the behavior. Axis A trajectories are what we call agentic. In an Axis A trace, the language model itself is the one emitting the tool calls.
Okay, so the AI is in control.
Right. The internal policy of where to search next, when to look at the shop rating, when to stop and verify, that entire decision tree lives inside the AI's neural network.
Wait, if Axis A is the AI actually making the decisions? Are you saying there's a scenario where the AI isn't doing the work? What is Axis B?
Axis B trajectories are what we call subtask. In these cases, the developer didn't rely on the AI to navigate. They wrote surrounding rigid Python code that emits the tool calls.
Oh, I see.
The Python code runs a deterministic, hard-coded search loop, and the AI is just invoked as a narrow classifier or a narrator to read the results of the Python script. The AI isn't making the decisions. The if-then statements in the Python code are.
Here's where it gets really interesting. Let me make sure I'm picturing this right. So Axis A is like a true self-driving car. The AI is scanning the road, turning the steering wheel, hitting the brakes, making all of the complex choices.
Yes.
But Axis B is like putting a car on a roller coaster track.
Right.
The steel track is doing all the steering and controlling the speed, and the AI is just sitting in the passenger seat with a microphone, acting like a tour guide, pointing out the window, saying, "Oh, look at that product on the left."
That is a brilliant way to conceptualize it. And the implication for training a new model is massive. If you train a new, blank AI model on Axis B data, it just learns to narrate the scenery.
Wow.
It becomes a fantastic intent classifier, but it never learns the underlying policy of how to search. It never learns how to drive the car. Therefore, the researchers had to be ruthless. They strictly filtered the daily fire hose to keep only the pure Axis A trajectories for their training corpus.
So they toss out all the roller coaster tour guide data, no matter how accurate the final result was, and they only keep the self-driving car data.
Exactly.
So once they have this pristine, judged, purely agentic training corpus, what exactly do they do with it?
They feed it into a small open-source base model called Qwen34B, but they don't just show it the data once. They put the model through an intense 5-stage post-training gauntlet.
Walk us through that gauntlet. How do you actually forge a shopping agent?
It starts with supervised fine-tuning, or SFT, where the model simply studies the filtered trajectories. Then they move to rejection-sampled re-SFT.
What does that mean?
Instead of just studying, the model is forced to practice multiple rollouts of a problem. They throw away the mistakes, keep only the flawless runs, and fine-tune it again on its own perfect practice.
Basically building muscle memory.
Exactly. Then there's continued teacher SFT, followed by a stage called KTO preference refinement. This is where they adjust the model's behavior, teaching it not just the right move, but the most efficient, elegant move without trying to expand its underlying knowledge base.
Got it.
And finally, they hit the most critical step of all, Dr. GRPO turn-level reinforcement learning.
Dr. GRPO. It sounds like a villain from a comic book. What makes this specific reinforcement learning so special?
It's actually a massive breakthrough. Think about how traditional reinforcement learning works. Usually an AI navigates a maze, and if it reaches the cheese at the end, it gets a reward. If it doesn't, it gets nothing.
Right.
But in a 15-step shopping task, the AI might make 14 brilliant decisions and one fatal mistake at the very end. Traditional RL would penalize the entire run.
Which is incredibly inefficient. Doesn't know which step was the bad one.
Exactly. Dr. GRPO applies a dense per-token gradient. It acts like a meticulous coach pausing the game tape. It can look at that 15-step trajectory, pinpoint the exact moment at step 12 where the AI made a bad tool call, and penalize just that specific step.
Oh, wow.
Yeah, while still heavily rewarding the 11 brilliant steps that came before it.
Okay, so they run this relatively small Qwen3 model through this intense 5-stage gauntlet using the pure data from the gladiator arena. What are the actual results?
The transformation is striking. Before this training, the raw base model had a dismal 18.0% average success rate on the held-out problem set. After this training pipeline, it rocketed up to 42.7% average success rate.
Going from 18 to 42.7, that is a massive jump for a small model.
It is. It's a 24.7-point gain, which lands it within a single point of the published synthetic data baseline of 43.6%. And here is the crazy part. It achieved this parity while using just a tiny fraction of a single day of the subnet's output.
I hear that, and I understand the technical achievement, but I want you to really think about that 42.7% number for a second. Practically speaking, in the real world, that means the AI still completely fails over half the time you ask it to buy something. If you hired a human personal shopper, and they got your order completely wrong 57% of the time, you wouldn't celebrate them. You'd fire them immediately. Why is 42.7% a victory?
It's a completely fair critique of the current state of AI, but you have to understand how brutal the ShoppingBench scoring is. There is zero partial credit.
None.
None. If the AI successfully finds the exact black waste bag, it's exactly under $20 and it's from a highly rated shop. But the shipping terms aren't exactly what you specified in your prompt. It scores a 0. It requires a perfect price, perfect service, perfect STU, and perfect attribute match simultaneously.
Okay, so it's less about the AI being stupid and more about the test being incredibly unforgiving.
Exactly. But there's another metric that tells a much more optimistic story, and it's what researchers call latent headroom.
What does that mean? The knowledge is in there, it's just stuff.
Spot on. The researchers measured the pass at 8 rate. This means if the model is given 8 attempts to solve the problem, does it get it perfectly right at least once?
And did it?
Yes. The pass at 8 rate was 53.3% compared to a first try pass rate of 34.8%.
That is a huge gap.
It tells us that the model's neural network has the underlying capability to find the right answer. The knowledge is in the brain. It just needs better extraction. That's why that Dr. GRPO reinforcement learning step is so vital. It provides those dense per-step rewards to convert that latent hidden ability into actual exact match conversion on the very first try. The curve is still climbing. They just need to run the reinforcement learning longer.
Okay, but that brings us to the elephant in the room. The paper states that they achieved this massive jump using just a tiny fraction of a single day's data from the arena. The obvious question any developer would ask is, why not just use more data? If a little bit of data got them to 42%, why not take a whole month of arena data, dump it into the model, and hit 80%?
Because of a fascinating quirk in human behavior and economic incentives. When the researchers audited the arena, they found a massive, unexpected twist.
Oh boy.
They looked at the top miner on the SN15 leaderboard, the developer taking home the lion's share of the crypto tokens. That miner had a staggering 77.3% average success rate.
Whoa. So there is an agent out there absolutely crushing the benchmark. They must have built some incredible neural architecture.
That's what you would think. But when the researchers pulled back the curtain and audited the embargoed source code of that winning agent, it wasn't a brilliant generalized neural network at all.
What was it?
It was roughly 1,850 lines of boring old-school Python code doing all the heavy lifting. The developer was using the LLM merely as a narrow intent classifier.
Wait, it was an axis B trajectory?
Exactly. It was the roller coaster tour guide. The Python code was driving the car, executing hard-coded deterministic search loops, and the AI was just sitting in the passenger seat saying, yep, that looks like a shoe.
So what does this all mean? Did the miners basically cheat the system? Instead of building the true generalized AI agents that the researchers so desperately wanted, they just wrote a giant spreadsheet of if-then statements to game the test and win the money.
It feels like cheating, but it's not. The miners are acting entirely rationally against the incentives they were given. Under the current scoring system of the arena, an Axis B hybrid approach simply outscores a pure Axis A neural network. It's more reliable. As a result, the leaderboard reliably converges on this pattern.
And because the leaderboard converges on that pattern, the daily fire hose of data is completely skewed.
Massively skewed. If we connect this to the bigger picture, of the 12,000 to 27,000 trajectories produced every single day, the vast majority are Axis B.
Wow.
They are structurally useless for training a self-driving agentic AI. The researchers were forced to throw almost all of the daily data away, which is exactly why they were training on such a tiny fraction.
That is tragic. They built this incredible, continuous gladiator arena. It worked perfectly to generate data. But the gladiators all figured out it was easier to bring a gun to a sword fight, and now the data's the wrong shape. How do they possibly fix that?
The paper outlines a really clever, two-pronged approach for the future. The first fix is on the arena side. They are going to change the scoring mechanism to explicitly reward agentic richness.
The meaning what?
Basically, they will financially incentivize miners to build Access A models, shifting the fire hose of the source.
Force the rules of the arena to favor the neural network over the Python script. Oh, that makes sense.
But the second solution is where it gets really sci-fi. They have this massive mountain of discarded Access B data reel verified tool calls that successfully found products. They propose using a strong frontier LLM to automatically rewrite those Access B traces into Access A formats.
I need to wrap my head around this. They're going to take the rigid Python logs and have another AI synthesize internal natural language reasoning between the steps.
Precisely. They are going to retroactively give the AI the inner monologue it would have had if it had driven the car itself. It turns real, verified tool calls into synthetic internal reasoning.
They are inceptioning the AI.
Exactly. And if they can pull that off, if they can unlock that massive Access B fire hose and feed it into the training pipeline, the model's capabilities won't just climb, they will skyrocket. We are looking at a near future where small, open-source models running on your laptop could completely match the capabilities of closed, massive models for specific, real-world tasks.
This has been an absolutely mind-bending look at how the sausage is made in modern AI. To build an AI that actually does things for you, the cutting edge isn't just making models bigger, it's moving toward continuous economically incentivized arenas where models fight to solve real-world problems, and we scrape the verified traces of their battles to train the next generation.
It is the ultimate evolutionary pressure cooker for artificial intelligence.
But I want to leave you with a final thought to mull over. We talked about how an LLM reasoning judge is the ultimate arbiter of who gets paid in these crypto arenas. The AI has to show the judge its math to get the money. Well, what happens when the miner agents realize they're in a simulation?
Oh, wow.
Will these AI agents eventually stop trying to be genuinely good at shopping and instead evolve specifically to psychologically manipulate the LLM judge into giving them a perfect reasoning coefficient?
It's a terrifying and entirely plausible next step in the arms race.
Something to think about the next time you ask a chatbot to buy you socks. Thank you for joining us on this deep dive. Keep questioning how the tools you use every day are actually built, and maybe next time be a little more forgiving when that brilliant AI turns back into a toddler trying to parallel park.